I want to start with a confession. I have always believed, like almost religiously, that the feeling of fullness was just a math equation.
Just volume.
Just
Awesome.
volume. If I want to stop being hungry, I need to fill the tank. I need a huge salad. I need fiber. I need carbs to physically push against my stomach so my brain gets that message, okay, we're done here.
That is the standard operating procedure.
Yeah.
We're taught that satiety is pure mechanics. It's about stretching the organ.
Right. But the research we're looking at today suggests that model is, well, if not wrong, at least incredibly incomplete. We're doing a technical deep dive into the physiology of an all-meat diet. Zero fiber, zero plant.
Carnivore diet, yeah.
And the thing that just leaps out isn't just weight loss, it's that people, they stop thinking about food. They report this profound silence where their hunger used to be.
The absence of appetite phenomena.
Exactly. And it makes absolutely no sense if you stick to that old volume theory. How can a 12-ounce ribeye, which has zero fiber and takes up way less space than a giant bowl of kale, keep someone full for 10 hours?
Right. The sources we have today, they focus on the physiological and neuroendocrine orchestration of satiety, which is a mouthful, but essentially we're looking at the chemical breaks, not the mechanical ones.
We're going to be talking about a very specific sequence of events. It's a technical tour of that gut-brain axis. And what the literature shows is that there are two distinct braking systems, a proximal brake and a distal brake.
And these breaks, what's fascinating is they don't seem to care about fiber.
No, they care about peptide signaling.
So the mission for this deep dive is to figure out how that machinery actually works. We need to understand why a piece of steak triggers this whole hormonal cascade, things like cholecystokinin, PYY, even GLP-1 in a way that, say, a bowl of oatmeal just can't.
And, maybe more importantly, how removing carbs might actually repair the sensors that tell us when to stop eating in the first place.
It's less about filling the void.
And more about flipping a switch.
Okay, so let's get into the wiring. The sources talk about a proximal brake. Proximal meaning what? Near or early? Right, this is the immediate signal, the first thing that happens. And the primary driver here is a hormone called cholecystokinin, or CCK.
CCK, I feel like I've heard of that, but only in a Bio 101 kind of context. It's just a digestion helper, right?
It is, but its role in satiety is, well, it's much more aggressive than just helping. CCK is secreted by what are called eye cells.
Eye cells.
And these are specialized cells located in the duodenum and the jejunum, so basically the very first stretch of your small intestine.
So these eye cells are like the frontline scouts. They're the first ones to see what's coming out of the stomach.
They're literally tasting the chyme, yes.
Yeah.
And here's the critical part that, gets back to your volume question. These eye cells are incredibly picky.
Picky how?
They don't respond strongly to carbohydrates.
Yeah.
You can flood your gut with glucose or bulky fiber,
Yeah.
and the eye cells, they're relatively quiet. But if you introduce long-chain fatty acids from hydrolyzed fat or amino acids from protein, they wake up.
Okay, so is this why the Chinese food syndrome happens? You eat a mountain of rice, you feel physically stuffed for maybe 20 minutes, and then an hour later you're starving.
The eye cells never pull the alarm.
Exactly. You triggered the stretch sensors, the mechanoreceptors, but you never hit the chemical brake.
Precisely. And the research we're looking at highlights how long this effect lasts. On a standard high-carb diet, CCK just spikes and then drops really fast. It's a blip.
But on a high-protein, high-fat meal...
Like a carnivore meal, plasma CCK behaves very differently. The numbers in one study were pretty stark. It showed plasma CCK rising to something like 5 to 8 picomolar.
And staying there. That's the key, right?
That's the key. It's not just the amplitude, it's the duration. In these high-protein contexts, CCK stays elevated for 3 to 5 hours.
That is a massive window. So for up to 5 hours, this hormone is just circulating. What is it physically doing to kill your appetite?
It's doing two big things. First, it binds to CCK1 receptors on the vagus nerve, which we can get to later. But the really mechanical part is it controls the pyloric sphincter.
The gatekeeper at the bottom of the stomach.
Correct. When CCK is high, it causes that sphincter to constrict. It narrows the exit. This drastically slows down gastric emptying.
Oh, wow. So that volume fullness I was talking about, you actually get that with less food because the food you did eat is being held in the stomach for much, much longer.
It's a biological timer. The steak hits the eye cells. The eye cells say, hey, this is high-value fuel, and they effectively shut the door to the stomach to make sure it trickles out nice and slow.
It turns your stomach into a slow-release energy capsule.
Whereas with processed carbs, the door stays wide open, energy floods your blood, insulin spikes, and the stomach's empty again in, 45 minutes?
Which explains the constant urge to snack. Of course you want a granola bar if your stomach is physically empty every 90 minutes.
But that proximal brake, the CCK, that's only the first line of defense. It handles the immediate post-meal window. If we want to understand why people claim they can go 12, even 16 hours without food noise, we have to look further down the line.
To the distal brake.
We need the distal brake.
And distal means further down, lower
Right.
intestine, the colon. The sources call this the ileal brake.
Yes, and this involves the L cells. These cells produce two other heavy hitters, peptide YY, or PYY, and glucagon-like peptide-1, GLP-1.
Okay, we have to pause on GLP-1 because right now the entire world is obsessed with GLP-1 agonists.
Ozempic, Wegovy.
Right, and we always associate GLP-1 with insulin and blood sugar. Are you telling me this is a meat thing too?
It is very much a protein thing. This is a huge misconception. We think of GLP-1 as an incretin, something that ramps up insulin when you eat carbs. But the L cells respond very robustly to peptide breakdown products and fatty acids.
So you don't necessarily need the drug to get the hormone.
Not if you're giving the body the substrate it's designed to recognize, and the timing here is it's fascinating. If CCK is the sprinter, PYY and GLP-1 are the marathon runners.
Okay.
TYY levels peak around 90 minutes after eating. GLP-1 peaks closer to 2 hours.
So it's like a relay race. CCK is handing the baton off right as it starts to fade.
Exactly. And the study data is so compelling here. There was a crossover trial mentioned where they manipulated the macros. They found that meals with 60% protein, which is very high, basically a carnivore ratio.
Almost impossible to eat that much.
It's self-limiting. You can't binge on sirloin the way you can on chips. But they found that meal induced significantly higher PYY releases than high-fat or high-carb meals of the exact same caloric value.
And that PYY release, that's what they call intermeal satiety.
Yeah, the gap effect. This second wave of hormones basically just shuts down the drive to eat for hours after digestion has moved past the stomach. It numbs the hunger signal from the bottom up.
And because of that slow gastric emptying from the CCK, the protein is trickling down to these L cells for hours.
Give you this steady, low-grade stimulation of GLP-1 and PYY that lasts all afternoon.
Okay, so we have the brakes, we have the stop signals, but we have to talk about the other side of this, the go signal, ghrelin.
The hunger hormone, the orexigenic hormone, the only one that actively screams at you to eat.
Yeah, the sources describe ghrelin as the starvation alarm. And usually whenever people go on a diet, any diet, and start losing weight, ghrelin goes through the roof. It's the body fighting back.
It's a survival mechanism. Your hypothalamus assumes you're in a famine, so it ramps up ghrelin to force you to go find food. It's why 95% of diets fail. Your willpower just snaps because that chemical alarm is too loud.
But this is where the carnivore and keto literature claims to have a metabolic advantage. How do you lose weight without the alarm going off?
You change the fuel source. When you restrict carbs to near zero, you enter nutritional ketosis. Your liver starts pumping out ketone bodies, specifically beta-hydroxybutyrate or BHB.
And we know BHB is fuel for the brain when there's no glucose.
It is fuel, but we're learning it's also a potent signaling molecule. It's almost like a hormone itself. And the research shows that BHB acts directly on the hypothalamus to suppress ghrelin output.
Wait, so the presence of the backup fuel tells the brain to just be quiet about being hungry.
That's a great way to put it, yeah. The study cited looked at people with a ketonemia of about 3.3 millimolar. That's deep ketosis.
Okay.
And even though they were in a huge caloric deficit, their ghrelin levels were lower than baseline, and their subjective desire to eat was blunted.
That is so counterintuitive.
Yeah.
A deficit usually equals hunger pangs.
It's like metabolic gaslighting, but in a good way. The BHB convinces the brain there's plenty of energy available, which there is on your body, so there's no need to panic.
The notes also mention something called LEAP2.
Yeah, LEAP2 is the antagonist to ghrelin. So think of ghrelin as the key that starts the hunger engine. LEAP2 is like gum in the lock. It blocks ghrelin from binding to its receptor.
Okay.
In obesity, and especially in high insulin states, the production of LEAP2 drops. You lose the gum, so the key works way too well. You become hypersensitive to ghrelin.
Uh-huh.
But the data suggests ketosis helps restore LAP2 levels. So not only are you making less ghrelin, but the receptors are being blocked more effectively too.
That explains why people on this diet don't get hangry. You know, that feeling shaky, irritable, desperate? That's a glucose crash plus a ghrelin spike if you remove both.
You get stability, a flat emotional line when it comes to food.
Which brings us to the elephant in the room. This is all meal-to-meal hunger. What about the long-term stuff? We have to talk about leptin.
The lipostat. the body fat regulator.
Right. Leptin is supposed to be the master controller. Your fat cells release leptin. More fat equals more leptin. And high leptin is supposed to tell the brain, hey, we are obese, stop eating.
That's the theory.
But if that actually worked, obesity wouldn't exist. An obese person has tons of leptin. Why is their brain not getting the memo?
Leptin resistance. And the source material points the finger squarely at one culprit, insulin. This is the insulin-leptin axis.
And the sources described it like a physical blockage.
It appears to be. Leptin's a big molecule. It has to be actively transported across the blood-brain barrier to get to the hypothalamus. And the research suggests that hyperinsulinemia, chronically high insulin from a high-carb diet, physically interferes with that transport.
So insulin is literally jamming the door at the blood-brain barrier.
It's blocking the signal. So you have a person with plenty of body fat and tons of leptin in their blood, but their brain is seeing zero leptin.
So the brain thinks it's starving.
The brain thinks the body has 0% body fat.
Yeah.
It's terrifying. It thinks it's starving, so it turns down the metabolism and cranks up the hunger signals.
It goes into energy conservation mode, which is why just eating less is torture for someone with insulin resistance. Their brain is already convinced they're dying.
So how does the carnivore approach fix the sensor?
It flatlines insulin.
Exactly. By removing the carbs, you drop insulin to basal levels, you remove that blockage at the blood-brain barrier.
And suddenly the leptin floods in.
The signal reconnects. The brain finally sees all the body fat. It goes, oh, wait a minute, we have 100,000 calories of stored energy here. We don't need dinner.
The sources called this the carnivore connection. It's basically resensitizing the dashboard.
There's a compelling evolutionary argument here, too. The thrifty genotype hypothesis. It suggests humans might be predisposed to become insulin-resistant during times of plenty, like summer, to store fat for winter.
But in our world, it's always summer.
We're always drowning in glucose, we're running Ice Age software in a candy store, and the hardware is just overheating. The carnivore diet, in this view, is just a return to the low insulin state that the machinery was built for.
I want to circle back to the wiring for a second. We mentioned the vagus nerve. The sources talked about something called metabolic endotoxemia. That sounds bad.
It's basically inflammation of the communication lines. The vagus nerve is 80% afferent. It sends signals from the gut to the brain. But the modern Western diet can actually damage that nerve.
How does a diet damage a nerve?
It starts in the microbiome. When you feed your gut bacteria a constant stream of sugar and processed fats, you get an overgrowth of certain gram-negative bacteria. Their cell walls are made of lipopolysaccharides, or LPS.
LPS is an endotoxin.
It is. And if your gut lining is compromised, leaky gut, that LPS gets into your bloodstream. It causes systemic inflammation, but it specifically inflames the vagus nerve.
So it's static on the phone line?
It cuts the connection.
Yeah.
So even if your eye cells are screaming, CCK, satiety, the message dies before it reaches the brain. By removing the fermentable fibers and sugars that feed those specific bacteria, the carnivore diet reduces the LPS load.
You clear the static.
You let the nerve heal.
Yeah.
And suddenly those satiety signals start getting through again.
There's one last mechanism in the notes that I found really interesting because it finally explains the meat sweats.
Yeah.
The aminostatic hypothesis.
Ah, yes. The idea that the body specifically monitors amino acid levels. Protein is metabolic currency, but it is expensive to handle.
Expensive in terms of energy.
Yes. The thermic effect of food, or TT. To digest protein, your body burns about 20 to 30% of the calories in the protein itself. Compare that to fat, which is like 0 to 3%.
When I eat a steak, my body has to work hard to process it.
It generates a lot of heat. It demands oxygen. The hypothalamus senses this metabolic cost. It senses the rise in amino acids in the blood, and it interprets this as a very strong stop signal.
You physically can't overeat it.
You can't. The metabolic feedback loop is just too strong. You hit a wall, you get the sweats, you get the heavy breathing, and you just put the fork down.
So when we zoom out and look at this symphony of satiety, it's not one thing. It's a multi-layered defense system.
It is a failsafe built on a failsafe. You have the immediate CCK brake locking the stomach. You have the delayed PYY brake, making sure you don't snack.
Yeah.
You have ketones suppressing the ghrelin siren.
You have low insulin letting leptin finally talk to the brain.
And you have the repair of the vagus nerve itself.
It effectively silences the food noise. And I think that's the part that really resonates with people. It's not just about weight loss. It's about mental freedom.
The sources refer to it as a hedonic reset.
Right. And that brings me to the thought I've been stuck on all day. We tend to think of our cravings as us, I'm a person who loves chocolate, or I just have no willpower. We treat it like a character flaw.
But the biochemistry suggests something very different.
Exactly. If our hormones are dictating our taste preferences, if high insulin makes us crave sugar and leptin resistance makes us insatiable, then are those cravings actually us? Or are they just symptoms of a broken, confused hormonal system?
It forces you to question the whole idea of free will when it comes to eating.
Mm.
If you fix the signaling, if you realign the biology, the personality of the eater changes.
You're not fighting yourself anymore.
You're just operating on a different set of instructions.
It suggests the path to dietary freedom isn't about white-knuckling it. It's about fixing the sensors so the machine runs on autopilot the way it was designed to.
And that is a very liberating thought.
A fascinating deep dive into the machinery of hunger. Thanks for unpacking all that with me.
Always a pleasure.